Hello everyone, welcome to lecture number 26, Fundamental Theorem of Calculus. You can think of this as the crowning achievement of this course. As you can see from the little symbol that I include here, this is going to be a theorem relating integrals and derivatives. So let's just briefly recap some important things that we've been talking about lately. We've talked about this one first, the indefinite integrals. So given a continuous function little f, an antiderivative, also called indefinite integral of little f. By definition, what is that? It is a function big F whose derivative is little f. And we denote it using this particular symbol here called the indefinite integral. It's an integral without any numbers here. Then we talked about something that in principle doesn't look like it's related to this in any way. It's the idea of the area below the graph, and that's the definite integral. So given a continuous function, little f, on a certain interval from a to b, the definite integral represents the signed area. We say signed because it's supposed to be negative if it's below the x-axis, positive if above. So the signed area between the graph of f and the interval ab. So if you have a function like this maybe, and let's say this is your a, this is your b, then the integral between a and b would be this green area here because that's above the graph, above the x-axis, minus this orange area below the x-axis. So the area determined by the graph of the function f. And we talked about how you can actually approximate the value of this area for general functions like this one that I just drew, which are not simple geometric constructs. And it's the idea of the Riemann sums. So if you have a partition of the interval, a bunch of points, x0 all the way to xn, and you also select some sample points, I call them xi star, they are between the xi minus 1 and xi, then you can construct this kind of object here, which you can probably think about more easily in these terms here. It's a sum where you look at the difference between the points that you're selecting, the xi points, and you multiply each one by the value of the function at the sample point, xi star. Then you add all those up. This is called the Riemann sum of that partition, and this is going to be an approximation to the integral. You can get the exact value by definition by looking at limits of such sums, which is something that I'm going to discuss during recitation this week. But the idea should be clear. We already discussed at least the Riemann sum. All that's left to do is discuss the limits of Riemann sums. But let me just quickly draw here. Imagine you have a function, once again, between a and b. And you want to somehow define what is the area between the graph and the x-axis. In such cases like this, where the function is a general curve, what you do is you subdivide this into very small pieces. Those are your xi points. And in between each one, you're also going to select an xi star that determines the height that you're going to select for each piece by looking at the graph of f. So in each one of these pieces, you're going to consider a rectangle whose height is determined by the value of, that's the thing that we call xi star. So you look at f of xi star, here's f of xi star. So you're going to be looking at a rectangle, very narrow rectangle like this, and you're going to add up the areas of all these rectangles. That's a good approximation for the integral. But that's not the topic for today, because basically nobody ever wants to compute areas like this by doing this approximation scheme. It's just a lot of work, a lot of calculation. What we're going to do today is a practical way to calculate the exact value of areas using antiderivatives. So using this first concept that I just talked about. And it's much easier than doing the Riemann sums. That's the concept of the fundamental theorem of calculus. So let's move to that. What we are going to consider first is something that's called the area function. So given a continuous function, little f, and also some fixed point A in the domain. The area function, let's say it's going to be defined only for x larger than or equal to A. It's by definition this particular expression here. It measures the signed area between the graph of f and the segment from A to x on the x-axis. So basically what we want to do is we want to put a variable as the upper endpoint of integration. Notice that this t inside is just the variable of integration. This could be any letter except x. A is also considered to be fixed down here, and it's the x that's allowed to move. That's the one that's going to be the variable of the function. And we're only going to consider x larger than a, but in principle, there's no reason to do that. You have some fixed a, and you have some function. For every x that you select, you can talk about this signed area. Once again, if x is right here where I put it, then this a of x function would mean the green area minus the orange area. That's what I'm going to write in here, green minus orange. But the idea now is that we want to consider this x as a variable. Think of it as something that can change. Okay, so the remark that I have down here is the same that I just said. In the function a, the variable is x, because as x changes, so does the value of a. Here's the x. The variable t inside is just a variable of integration, and you can call that anything you want except x or a if you really want to be pedantic, like this little a is also being used. So yeah, you can write the a of x function also as this, for example. That's the same thing, where I changed the variable of integration to y. Or you can also define this function as, let's write its variable as w, because why not? So you have a w instead of x up there. This is all the same expression. All right, so we have already talked about this function before when we defined the definite integrals. We just never gave it a name of area function. But this is the same type of problem that we already did. Consider this particular piecewise function. It's constant before x3, and then becomes some linear function after x equals 3. Use geometry to compute the area function based at the point 0. And considering only the domain x larger than or equal to 0. So we have our function little f here. I drew the graph for you. And we are now talking about this area between 0 and some value x. The only difference between this problem and the types of problems that we already did is that before we would have just some number up here, like the number 2, and I would ask, what is this area? It's going to be a number. This time I have an x, and I want you to write this as an expression of x, so it gives you a function. What is the idea? We have to consider, imagine your x is going to be some number larger than 0. If it is right here, before the number 3, then that should be a very easy calculation. A of x represents this area right here, this rectangle. And it's some positive area because the function is above the x-axis. What is this area? That would actually be base is equal to x and height is equal to 4, so 4 times x. So right from here, we understand a of x is equal to 4x if x is less than, or you can also say less than or equal to 3. This formula is going to be valid up to x equal to 3. But if x is larger than 3, then we start having more area. Imagine here now, if x is here, you're also going to have this trapezoid part. So I'm going to draw the picture again so we can put the x later after 3. Here is the graph. Imagine now you have some x in here instead. Here's the number 3, here's the number 4. And if you remember, this piece of the function was given by 2x minus 2. That's the function. Oh, well, so what does that mean? It means that the height of this y value right here, the location above the point x, is equal to 2x minus 2. So now we are talking about this whole area, this rectangle plus this trapezoid. What is this area? Well, the rectangle is 12. because you have 3 times 4. And the trapezoid is going to depend on x. If you remember area of a trapezoid, you have to add the 2 bases, the 2 parallel sides. So let's do that. This one is a length of 4. This one is 2x minus 2. 4 plus 2x minus 2. Now you multiply that by the height, which is the line segment perpendicular to both bases. How much is this height? It's x minus 3. I hope you agree with that. X would be the entire length of this segment, but then you also have 3 here. So this one that we are talking about is x minus 3. And you finally also have to divide the whole thing by 2. This is the area of a trapezoid. So what does that become? You can simplify here. This is going to be 2x plus 2 divided by 2 will give you just x plus 1. So the a of x in this case is, remember there was already this area of rectangle, and now there's also this piece of the trapezoid. So this is true if x is more than 3. We have our answer then for the area function. Before it was just 4x. And now after x equals 3, it becomes this particular expression. So I hope this just gives you the idea that area function is a function, depends on x. So you have a function f minus 2x plus 1. And I'm going to give you 2 different area functions, a1 and a2. For the same f, looking here, I use the letter s for the integration because you can use whatever letter you want. The only difference between a1 and a2 is the place where it starts. a1 starts at 1, a2 starts at 2. But they both are area functions. They go up to x. So use geometry to compute the following area functions. Let's do that. Here's the f function again. It was a line segment minus 2x plus 1 with a negative slope. And if you do the math, you're going to see it crosses the x-axis at x equals 1/2. So let's try to think first of all about the area function starting at 1. Imagine you have some point x now larger than 1. Let's say here. What is the area function now? Well, I should technically be doing this in orange to be consistent with what I did before. But the area function is actually the negative of this area. And that's the area function that we called a1. The one that starts at 1 is the negative of this area. So we just have to compute that. That's trapezoid area once again, but I'm going to put a negative sign for it. So let's compute this trapezoid area. Let me draw it a little bigger so we can draw the side lengths for everything. What is the height of this trapezoid? Up here, that would be x minus 1. Just look along the x-axis. This segment is x minus 1. What is the smallest base? The smaller base here. Well, this point on the graph, it is on the graph of the function f, corresponding to the x value 1. The function is minus 2x plus 1, right? So the value here is going to be equal to minus 2 times 1 plus 1. That's the number minus 1. So if this segment here is equal to minus 1, the coordinate of this point is equal to minus 1, that means that the length of this segment is 1. Lengths have to be positive, right? So all I'm saying is that because this is the point of y coordinate equal minus 1, that means that the length of this piece is 1. And then similarly, what is it for the other part? F of x would be minus 2x plus 1. That's, however, a negative number. Then what is the length of this entire segment? just take the negative of that negative number. So 2x minus 1, sorry. Those are the measures on this trapezoid. So we're going to calculate this area. Remember how you do that? Add the bases, multiply by the height, divide by 2. This is going to be just 2x divided by 2 is just x. And I'm going to write 1 minus x instead of x minus 1 because of the minus sign. So this is a1 of x. Now we're going to compute a2. The question was also asking about that. Maybe I use the same drawing here. Well, no, let's forget about that. Okay. Here is once again the function little f. Now we are talking about the number 2 instead of the number 1. So imagine you have some x larger than it. It's still a trapezoid. It's still the same reasoning. What happens is that a2 of x is now the negative of the area of this trapezoid. So we have to do the same computations. So once again, height is x minus 2. And the basis, this large base is still the same. Remember what it was, 2x minus 1. This one, however, is computed at the number 2 instead of the number 1. What is the y coordinate corresponding to that? If you go back to the function was 1 minus 2x. That will give you 1 minus 4, so minus 3, which means that this space has a length of 3 this time, this one. Okay, but everything else is the same. Now you calculate this, you have 2x plus 2 this time, so x plus 1 after divided by 2, and times 2 minus x. Those are the functions a1 of x and a2 of x, which I can probably distribute the x just so we write them as polynomials. So here was a1, it's just x minus x squared. And a2, we just found it right here. What does that become? Let's see, you have minus x squared. You have 2x minus x, so just plus x. And then you have 1 times 2, that's plus 2. Those are the answers to item A. We found the area functions. Item B is now saying compute the derivatives of those functions and compare to the function little f. Little f is right here, minus 2x plus 1. Let's do that. That's going to be very easy. What is a1 prime? Look here, 1 minus 2x. What is a2 prime? Looking here now, minus 2x plus 1, and then this does not have a derivative. Okay, so minus 2x plus 1. Those are actually the same expression, both equal. Not only equal to the function f. F was 1 minus 2x, remember? Okay, so that's this example, and there is no coincidence here, by the way. So look at this, the area function, the derivative of it, gave you the little f that you used to compute it. Both of these actually gave you that same derivative, no matter where you started. So that is no coincidence. And this is the fundamental theorem of calculus, which, by the way, has 2 equivalent forms. This one we're going to be calling the first form. So how does that go? Suppose that little f is a continuous function, like the 1 minus 2x that we just had, on an interval, and then let little a be any point in the interval. Like in the problem before, we chose both little a equals 1 and 2. And now consider the area function based at that little a. As it turns out, it is always going to be a differentiable function. And if you calculate its derivative, you're going to find the function little f that is inside. In other words, the dx of this expression, the area function, is little f. at the point x, the same x that's above there. Fundamental theorem of calculus. This is how it works. And I'm going to give you just some idea of why proof. Maybe I write proof between quotes, just so we understand what is going on. So picture your function, the little f graph, something like that. Imagine you chose a point H to start with, computing your area function, doesn't matter where, and you have some x. I'm also going to write here an x plus h, where h is going to be some very small number. All right, so as it turns out, if you compute the area function on this x plus h and then subtract the x, the a of x, what is it geometrically? When you look at a of x plus h, you're talking about this whole area right here. And then you're going to subtract this area all the way up to x only, so only the first part. What do you get from here geometrically? You get this green area. So this is equal to the green area, which now we go back to this idea of the Riemann sums and Riemann the approximation to integrals. When you have a very narrow area like that, that is always approximately equal to the area of a rectangle. Let's say it's a rectangle of base h times what is the height that we can consider for this rectangle? Well, we can consider it to be f of anything inside of this interval. Remember the point that we usually call x star. But let's consider the x itself. Let's consider f of x, which is this height right here. So this is very much approximately this area. And let's divide by h now. I hope you see where I'm going with this now. This is approximately f of x. As it turns out, this approximation gets better and better the smaller you make this little h. Just imagine making little h smaller will make this rectangle even more narrow, meaning that this approximation by a rectangle area is better and better. And you can make this formal, we're not going to do that, but as it turns out, when you compute a limit as h goes to 0, so as h gets very small, it becomes actually equal, not just approximately equal. But what is this limit that we have on the left side here? That was our definition of what the derivative is at the point x, remember? This is the limit that defines a derivative. This expression inside is called the difference quotient. So we have right here the justification of why a prime is equal to little f, which is what the theorem says. That's the first form of the fundamental theorem of calculus. We are going to do some brief exercises about it. Those are always very easy. And then we're going to go to the second form, which is the one that's more important for us, the one that helps calculating integrals. But first of all, let's look at these exercises. Calculate these three items here. The first one will be very easy. You just have to realize what is it that we have. You're taking an x derivative of this particular expression. This expression is exactly the area function because you have an x upstairs and just a number downstairs. And what is the function that you're taking an area of? It's the cosine square of 3t. The derivative of the area function gives you that function at the location where you're taking the derivative, at this x in this case. So that's it. The derivative of this function is cosine square of 3x. Second item, what changed here between the first and the second? Just the location where you started. This is a different area function for the same little f, but you're just starting at a different point. But the theorem says it doesn't matter. The derivative will be exactly the same thing. Remember, it could be any little a, the starting location. For the integral could be any little a in the domain of the function little f. Well, this function has everything as domain, so that's okay. And finally, the third one, you have ddx, but what you have now, it's technically not an area function because the variable x is downstairs instead of upstairs. There is no problem about it being y instead of t. That's okay because that's just the variable of integration. The problem is in the location where x is. So what do you have to do first is this. Remember that by definition, when you switch the endpoints of integration, if you write x above and minus 4 below instead of the order that they came, what it means is it's just the negative of what it was. So I have this extra minus sign in front. And now this is okay. The derivative of something with a minus, first of all, the minus can come outside of the derivative. But now the thing that you are taking a derivative of, that one is an area function. X is upstairs. So what is this going to be? There's a minus, and then the function evaluated at x. That's all. So these were very simple examples. We have some slightly more complicated ones where the variable in the area function might be not just x or some function of x. In this case, there's a couple things going on. First of all, the variable of integration in this first item is x, and then the variable of the area function itself is r. These are just variable names, all right? But what is going on here? We have the function f of x equals root x, the function being integrated. And the area function of that as a function of some variable r, that would have been integral from 1 to r. This is an area function, right? You just go up to that same variable. But what we have there is not a of r, it is a of r cubed. So what we want is the derivative with respect to, to the variable r of this expression, a of r cubed. Don't write that as a prime of r cubed. That is not the same thing. What you have to do is you're looking at a of r cubed. This whole expression here is a of r cubed. And then you're taking the derivative with respect to r of that entire expression. Why does that matter? Because this is a chain rule type of situation. You have some function of some other function. So what you have to do is a prime r cubed times 3r squared. You see that this is definitely not the same as just a prime of r cubed. But now this is okay because we know a prime of anything according to the fundamental theorem of calculus. A prime of anything, if that thing is r, is going to be square root of r. That's how the fundamental theorem of calculus works. So a prime of r cubed is going to be square root of r cubed. And that's the answer that you find for item A. All right, so what is the bottom line here? Just if you have an expression in one of the endpoints of integration, you're going to need some chain rule to calculate that, not just the fundamental theorem of calculus. And we're also going to have that in item B now. But there's one extra complication. The variable appears in both endpoints. So let's do B now. 2x to 3x sine of 5t. Okay, we have the function sine of 5t. And we don't actually have the area function of it. Area function has to start at a fixed location, but this one does not. So what we're going to do is split it up as two pieces. We're going to write this integral of f. You choose some number, doesn't matter which number, let's choose the number 0. As long as it's a number in the domain of the function. And you're going to split up the integral like this. Because that's how integrals work. If you want to integrate from a number to another, you can go from the initial number to any stopping point that you'd like. Doesn't matter if it's larger or smaller. And then you go from that stopping point to the number where you want it to go. You can always do this. And just so we have x's in the top instead of in the bottom, like here, we're going to flip the first one with a minus sign. And we're going to be calling these guys area functions with a base of 0. So this first one, there's a minus sign. First of all, this is the area function evaluated at the number 2x. And the second one is the area function evaluated at 3x. This is the expression that we originally have in the problem, right here, where f is the function sine of 5t. Now we want to find the x derivative of that. Well, the x derivative, d dx, of the expression that we just found, just do this by the chain rule. That's going to be minus a prime of 2x times 2 plus a prime of 3x times 3. I'm using the chain rule in each one of the terms. And the a prime function is the same as little f. That's the fundamental theorem of calculus. But you have to be, you still need to evaluate it at the correct location, 2x and 3x. Okay, so fundamental theorem of calculus entered right here. A prime equals f. And now let me just replace f with what it actually meant. Remember, f was the sine of 5t function. So if you're plugging in 2x for the argument of f, that it goes in the location of the t. And similarly for the other one, sine of 5 times the t, in this case is the 3x. And another times 3 in front. So let me just put all this together. You're going to have minus 2 sine of 10x plus 3 sine of 15x. This is the derivative of the given expression. Where is it? Yeah, here. So that's the trick that you do when you have derivatives involving the variable in both locations. You split up the integral into 2 pieces, stopping at some fixed number. But let's move on. Now we talk about the second form of the fundamental theorem of calculus. As I said, this is the one that's the most useful. The one that allows us to calculate integrals, calculate areas, without having to do Riemann sums. So I'm gonna state it in this way and then immediately talk about a slightly better form, but let little g be some differentiable function on an interval. Then if you take any 2 points a, b in that interval, the integral, the definite integral of g prime turns out to always be equal to g of b minus g of a. So when you integrate a derivative, this is a way that you can think about this. Derivatives and integrals are kind of the reverse operation. When you integrate a derivative, you get the original function, the g in this case, but it's not like it's g of x. That would not make any sense. What is x? X is just a variable of integration. As it turns out, it is g at the end points, one minus the other. This is fundamental theorem of calculus. I'm gonna just talk briefly about how to justify this. Once again, this is a proof between parentheses. Imagine that we call this big, let's say big G, as a function of b, this particular function, the integral of g prime, the one that appears in the theorem, as a function of b. This is an area function, all right? The variable is now b, it appears up here. A is considered as a parameter, and the function inside is g prime, but this is area function. So what have we just discussed about area functions? The fundamental theorem first form, it says that the derivative of an area function is equal to the function inside g prime at that same location, this b in this case. So we know this about this function because of the first form of the theorem, but we also know one important detail about it. What is big G of A? So we are considering it as a function of B. What happens if we plug B equals A? Well, then that's going to be an integral between A and A. And we talked about how integrals between one point and the same point, they are by definition always equal to 0. So do you recognize what is this now? This is IVP, initial value problem, for the function big G. We have its derivative formula. It's just that the variable is being called little b instead of x. And we also have one value at one specific point. So from the first one, we can find its value. The big G function is an antiderivative of whatever you have on the right side. I'm solving the IVP, db in this case instead of dx. But this is a very simple one to do, right? What is an antiderivative of g prime? Here you can see very clearly why integrals and derivatives cancel each other. They will give you a function whose derivative is g prime, that is the function g, plus some constant. And we determine the constant by plugging in into here. 0 is g of a, which according to this formula should be little g of a plus c. So the constant is equal to minus g of a. Just solving for c here. And I'll just plug this value of the constant up here. Big G is little g of b minus little g of a. That's the constant. Now just remember that big G was exactly the thing that we wanted, this definite integral. So we have just proved that this definite integral is equal to little g of b minus little g of a. All right, this is a proof using the first form of the theorem. That's why it's called another form of it. It follows from the other form. Or analogously, you could have proved this one first using Riemann sums and then concluded the first one. They are equivalent to each other. But this is really not important for us. Proving it's always going to be discussed because we are trying to understand what these things are, where they come from. But we have this theorem. You need to remember this. And now I'm going to just talk about a slightly better way to think of it. It's like this. Think of it this way. If you have some function little f being integrated, and if you know an antiderivative big F, then you can do it this way. Big F of b minus big F of a. Compare this to the way that we initially stated this. You're going to see this is exactly the same thing. We're just replacing g prime with little f, and then g with big F. So what is the relationship before? G prime is the derivative of little g, and now, well, little f is the derivative of big F, because that's what it means to say big F is an antiderivative. So this is just a matter of renaming the functions. It's still the same theorem, but that is the most important result here, the thing that we always want to remember. When you look at a definite integral like this for some function little f, what you have to do to calculate that is find an antiderivative big F, and then just evaluate it at the end points, one minus the other. This is how you calculate definite integrals without having to go over Riemann sums. So I'm just going to do some simple examples here, and then we'll be done. Calculate all of these integrals, and they all basically fit here. So if you're going between 0 and 1 for the function x squared, what you have to do is, first of all, find a function that's an antiderivative of x squared. That would be the function x cubed over 3. And then evaluate it between 1 and 0. So I'm going to just write this way. Big F of 1 minus big F of 0, where big F is the antiderivative, or a antiderivative of x squared, x cubed over 3. So that just becomes equal to, plug in 1 and 0 for this guy. You're going to have 1/3 minus 0. So that's just 1/3. This is an area that we are going to find in recitation, by the way, using Riemann sums. The area below the parabola between the x values 0 and 1. Imagine the parabola x squared. Here's 1. Here's 0. The area below a parabola, that's not really something that you can do with geometry. This is not a triangle or circle or trapezoid, anything like that. A parabola is just some curve, but it's possible to compute this area using Riemann sums, and we're also going to find the value 1/3. Okay, now, by the way, let me do that with the, let's do item C first. So you're integrating sine x between 0 and pi. So it's, you know what you have to do? First of all, find an antiderivative for the sine function. What is a function whose derivative is sine? That would be minus cosine. And instead of having to write it like this, like you choose a symbol, big F for minus cosine, it's very customary to do this, minus cosine. You put a big vertical bar and you write the endpoints here. What does that mean by definition? It means the function that you have inside evaluated at the upper number minus the lower number. It's exactly the same thing as this. It's just a slightly faster notation. All right. So what this means, it means the function minus cosine evaluated at the upper number pi minus the function minus cosine evaluated at the lower number 0. Just so you don't have to define a new function with a symbol and then write it like that. And what is this number going to be? Cosine of pi is minus 1 with an extra minus in front becomes plus 1. And here you have plus cosine of 0, which is 1. So that's a 2. Geometrically, this integral represents the area between 0 and pi of the graph is of the function sine. If you look at sine of x between 0 and pi, it looks like this. This is the sine function between them. We are now computing that the area of this piece of the graph is actually equal to the number 2. Once again, this is an area that you would not be able to compute geometrically. This is really not a circle. It's just a sine curve. Okay, so we can do item B now. I'll write it downstairs. You have 2 to the minus 3 of the function x. X dx. What is this integral? So find a function whose derivative is x. That would be x squared over 2. And evaluate it between the numbers 2 and minus 3. So that means evaluate it at the number minus 3 and then subtract at the number 2. What do you have? 9 over 2 minus 4 over 2, which is 5 over 2. Very simple. This problem was also saying compared to the answer that you get geometrically. So just imagine the function x. That one is a very simple function. It's being integrated between the numbers minus 3 and 2. This is f of x equals x. Okay, I'm going to use different colors here. The integral represents the, in this case, orange minus green. Orange minus green. The one above the x-axis minus the one below the x-axis. Try to compute this geometrically. Just find the areas of these triangles and do this calculation. You're going to see the number 5 over 2, unless we made some mistake. So I'm not going to complete this part. That's just geometry. What about this other one? Sine x between 0 and 2 pi. Well, the function whose derivative is sine is the function minus cosine. But now we have to evaluate it between 0 and 2 pi. So minus cosine of 2 pi minus cosine of 0. cosine of 2 pi and cosine of 0 are both 1. So this is giving you the number 0. That's the value of this integral. Why does that make sense? Let's go back to here, the graph of the sine function. If you look at the graph between 0 and 2 pi, well, now you're talking about this area as well. You're talking about the area above the x-axis minus the other one below. And just because of symmetry of this graph, those two areas are actually equal to each other. So when you compute one minus the other, you have a 0. That explains why we're finding a 0 here. And last one, I'm going to do this down here for space. I'm using this notation where the dt was part of the fraction. Remember that this just means 1 over t times dt, where x is some fixed number. So we're basically talking about the area function of the 1 over t little f. How does that work? What is a function whose antiderivative is 1 over t? ln of absolute value of t. Sorry, whose derivative is 1 over t. That is a function that works, and then you have to do that between 1 and x. You technically don't need the absolute value because these guys are all positive anyway. So this is going to be ln x minus ln 1, which is just ln x. So this is saying that when you look at the function 1 over t, between the number 1 and some number x, the area that you find under that graph is ln of x, which is a fact that you may have heard about already before. This could be considered the definition of the logarithm function. All right, so let's stop talking about these problems. My last remarks are, yeah, the two remarks here. First of all, the fundamental theorem of calculus says, if big F is an antiderivative of little f, then you can calculate the integral by doing precisely this. Big F at b minus big F at a. This is what we've just been doing. But we discussed before, remember that when you have functions on an interval, the family of antiderivatives of some little f, they are given by, they differ by constants. There is not just one antiderivative of the function little f. There are many others. So what happens if you, instead of using this big F, you use some other one, which is big F plus c? What happens if you use that antiderivative? The answer is it doesn't matter, because when you do this calculation here, the plus c's will go away anyway. So in other words, if you do g of b minus g of a, where g is big F plus c, then because of this minus sign, the c's go away. You still have the same thing as big F of b minus big F of a. So yeah, let me go back here. When we use the antiderivatives, for example, I told you antiderivative of sine is minus cosine. What if we use minus cosine plus 2? That's also an antiderivative. Doesn't matter. You don't need to add this plus c here because it's going to go away anyway when you do the minus. So that's one remark. And the other one is, we already discussed, convenient shorthand. Given some function, this symbol represents function at the upper number minus at the lower number. We already used that. So maybe that's enough about definite integrals for today. I'm going to leave this for the recitation, but you should try anyway. Try this problem, and I'll give you the answer during recitation so you can see if you got it right.